Okay, let's do several disk method examples. We'll do a couple rotating around the x-axis and a couple around the y-axis. So we have here some function y equals e to the x plus 1. So we should know, like we're in calculus 2, regular e to the x passes through 0, 1. Adding 1 to that, we're going to get a horizontal asymptote here. Sorry, at 1. And we're going to pass through the point 0, 2. So here is y equals e to the x plus 1. We're bounding that between x equals 0. So I'm going to put all my bounds here in red. X equals 0 is the y-axis. X equals 1. Y equals 0 is the x-axis. So I want that area there rotated around the x-axis. So let me see if I can draw this in blue. So if that's my top, my bottom is going to be down here at 2, have the same shape, and we're going to rotate this around like that. Let me exaggerate that a little less. There, hopefully you can see that. I'm not the best at drawing these. That's rotated around the x-axis. Anytime you're rotating around the x-axis, your disks are stacked along the x-axis. So maybe in green, I'll try to draw one of the disks that we're doing. And the volume of that disk is area of the base times height. The base is a circle. Area of a circle is pi r squared. R is this function height right there. So I'm out here at some position x. Look, I could just use the formula. We know the formula. When you rotate around the x-axis, this is the formula. You can just memorize this, but if you don't understand where it comes from, you're going to get all the different formulas confused. This is why I'm making such a big deal of making sure you understand what's going on. This right here is the area of that green, the cross-sectional green circle here at position X. So maybe let's try to draw that green circle over here. That radius right there, R, is f of x, which is e to the x plus 1. And that area is just pi r squared. So that'd be pi e to the x plus 1 squared. Okay, what were my starting and ending? What were the end caps of this thing? X equals 0 and x equals 1. Oops, no, I wanted that green is, it's a little too lime green, isn't it? So the integral from 0 to 1, pi r e to the x plus 1 in parentheses squared dx. So that's integral 0 to 1. I can bring the pi out. Remember, when you're squaring a binomial, e to the x plus 1 squared means to multiply that by itself. So that would be e to the x quantity squared, rules of exponents, a power raised to a power you multiply. So that's e to the 2x. Outer and inner, I get the same thing. So plus twice e to the x. And then last. Okay, now we're going to actually do this integral. Now we could, like, I could go through a whole bunch of details here and split this into 3 different integrals and do a U sub on this one. Like over here, maybe is some side work. We'll kind of talk about this. E to the 2x dx. I could go, well, let u be 2x, then du is 2dx. Oh, I've got my u here, but I don't have my du. I need a 2 here. Well, in order to put a 2, I need a 1/2. So this will be 1/2 antiderivative e to the u du, which is 1/2 e to the u plus c, of course, but we're doing a definite integral over here. I'll put it in. So that's 1/2 e to the 2x. Listen, we're supposed to be at this point right now that you can do some of these basic integration by substitution problems in your head. It's just true in general that the antiderivative of e to the ax dx is 1 over a e to the ax. And the way I want you to remember this, I know I'm going off on a tangent here, but this is important. The derivative of e to the ax, you pick up an extra a on top. You remember that from Calc 1. Well, when you're going backwards, because an antiderivative is just a backwards derivative, instead of picking up an a on top, you pick up an a on the bottom. The point with all of this is I don't need to go through all that to do this guy's antiderivative. You should just be quick enough to know that that's going to be e to the 2x over 2. Antiderivative of e to the x is just e to the x. Antiderivative of 1 is x. And that's all evaluated from x equals 0 to x equals 1. These are not all 0 at 0, so I do need to plug in both. So this pi is just going to hang out for a minute. Plug in the top, I'm going to get e squared over 2 plus 2e to the first plus 1 minus, I need this in parentheses when I'm plugging in 0. E to the 0 is just 1, because anything to the 0, any non-zero thing to the 0 power is 1. So I get 1/2. E to the 0 is 1, so plus 2 plus 0. Okay, and now I just got to be careful. Like, let's clean this up here, and then we'll distribute that minus. Let's see, so that would be 4/2 plus 1 more is 5/2, so minus 5/2. And then 1 minus 5/2, that would be 2/2 minus 5/2. That'll be negative 3/2. So 1 minus 5/2, so minus 3/2. And that should be our final answer. We could distribute the pi, but it's just as pretty like this. All right, let me pick another one. Okay, so we're still following the same directions here. We've got y as a function of x, and we're going to rotate this around the x-axis. So I'll write that in here, because we're going to do a couple in a minute that are around the y-axis. Always want to draw these out, always. So we've got 1 over x, and we're going from x equals 2 to x equals 3. So here is our region that we're rotating around. So our bottom here is going to look exactly like the top, but reflected over. Let me get that a little closer. So we're cutting them off here, and these are rotated around. Kind of make them look circular here, even kind of drawing a circle there. Okay, then, like again, if we just use our formula, we're rotating around the x-axis, and we have y as a function of x. This is the formula we're always going to use. I'm telling you that it helps to understand where the formula comes from. So I pick some random spot here, X. Then my cross-sectional area, which is what this is a circle. That blue circle there has area pi r squared. What is r? R is this distance here, 1 over x. All right, now we just plug everything in. So this will be the definite integral from 2 to 3. That's what we had, 2 to 3. Pi 1 over x squared. So the function squared dx. We can bring that pi out front. You're always going to do that. Just always don't forget it at the end, though. I see that happen sometimes. 1 over x squared dx. The antiderivative of 1 over x squared, so maybe over here on the side, we'll think of that as x to the negative 2 power. So I'm doing an indefinite integral over here just as some side work. Raise the power up by 1 and divide by the new power. And then, of course, we would have a plus c if we were doing an indefinite integral. Remember, no plus c's in definite integrals. So this will be pi times, I'm going to write that as negative x to the negative 1, which is 1 over x, evaluated from 2 to 3. Now, at this point, something should be clicking in your brain, and you should say, I think the professor just goofed. How are we going to get a negative answer? There's no way that volume can be negative. Your volume is never going to be negative. Don't worry, it's going to work out. We're still going to get a positive number. And the reason is if you put a bigger number in a fraction, the fraction becomes smaller. So this will be pi times plug in the top minus plug in the bottom. So negative 1/3 minus negative 1/2. So that's negative 1/3 plus a half. So 1/2 minus a third, this would be 3/6 minus 2/6, that would be 1/6. Our answer is pi over 6. It's an ugly 6. Isn't that kind of cool that this volume here is pi over 6? We'll talk later about the volume versus the length versus the surface area. If we start 1 over x at 1 and we go all the way to infinity, we have this infinitely long trumpet looking thing. And we'll see that there's this weird relationship between the infinite length, the volume, and the surface area. Two of those are infinite and one of them is finite. It's called Gabriel's trumpet. That's coming later. Okay, let's do a couple around the y-axis. Okay, so go ahead and read this. We're going to be rotating around the y-axis now. So if we're going to be rotating around the y-axis, this is very important. If you're rotating around the y-axis, because of that line right there, you need x to be some function of y. So you always need to solve x in terms of y. So let's kind of draw this out. So that's a line, right? When x equals 0, y is going to be 4. And let's see, when x equals 8, y will be 0. So I just kind of picked a couple numbers there, and we're going between x equals 0 and y equals 0. So we're going to take this region here and rotate it around the y-axis. So we'll get something similar over here. And Try to draw in some of these circles. So our discs are going to be stacked vertically now. See, we're going to have all these discs here. So the cross-sectional area of one of the discs, like this one right here, will be this distance here. I need that to be, well, x is a function of y because that's going to depend on my height, y right here. When you're rotating around the y-axis, you're integrating with respect to y, everything needs to be y's. When you're rotating around the x-axis, everything's in terms of x. The disks are all stacked up along the x-axis. You're integrating dx. You have f is a function of x. With the disk and washer methods, going around the x-axis, everything's x's. Going around the y-axis, everything's y's. That's all going to be backwards when we get to shell methods later. Okay, so I need x to be a function of y, which means I need to solve this guy for x. So let's see, that will be, yeah, let's just write it out and do it one step at a time. So we'll move the 4 over. Y minus 4 is negative 1/2 x. Multiplying both sides by negative 2, let's see, I think we're going to get 8 minus 2y equals x. So that's my g of y. But these swap places because that negative. Make sure you see what's going on there. Then, like our general formula, is we're going from C to D of pi times g of y. But my g's and y's don't look too much alike. Squared dy. We need to find C and D. These are my starting and ending y values. Notice they didn't tell me that. I had to draw the picture. If you don't draw the picture on these, you're going to get them wrong. I guarantee it. I had to draw the picture to see how high my y's were going to go, all the way up to 4. So here's C is y equals 0. Here's D is y equals, again, my g's and y's are looking a little similar here. 4. If you're rotating around the y-axis, everything is in terms of y. Your limits, your function, your differential here. So then my volume will be the definite integral from 0 to 4, pi, g of y, 8 minus 2y squared dy. Once you get here, this is the hard part, setting it up. Now it's just doing an integral. So like moving that over here. I can bring the pi out. Remember, squaring a binomial, the shortcut is square the first one, multiply these two together, and then double it. So that would be 16. Twice that would be negative 32. And then square this one. And it's always plus, same sign, plus. dy. Don't forget your dy. Remember, you will never in your life write an integral without having a differential over here. So that will equal pi times 64y minus 32y squared over 2, so 16y squared plus 4/3 y cubed, evaluated from y equals 0 to y equals 4. Okay, I may just throw this in my calculator. Let me show you how you would throw this in your calculator. Let me pause and open that. Now, you want to be really, really careful doing this. In fact, I might do it in stages. instead of typing it all in at once. Maybe I'll do it both ways just so you can see. But if you're not very careful typing this into your calculator, you're going to get the wrong answer. And then when I go to grade it, I don't have anything to grade because you didn't show all the intermediate steps here. So you got to be very careful if you're going to type this in your calculator. So this will be pi times, and I'm going to do the top. 64 times 4 minus 16 times 4 squared. Like we know that's 16, but I'm going to do 4 squared plus 4/3 times 4 cubed. So I can use my little caret here. Cubed. Now I could, like I was saying, I could just now do minus and then put in parentheses everybody. Oh, I guess that's being silly. Everybody at 0 is already 0. Look, everybody has a y. I don't have to do that. That's not always going to happen, but in this case, when I plug in 0, everybody's 0. So I don't even have to worry about that. This will just be my answer. Okay, now this is what's interesting. It's going to give me some decimal. Sometimes we'll leave it like that. But if I want to turn that into a fraction, I've got this button on my calculator that'll do that. I just hit math and number 1. I just hit enter. I hit enter twice. It'll turn that into a fraction. 256/3. Don't forget the pi. So my final answer is 256 pi over 3. All right, let's pick another one. Okay, so I just started to do this problem from your book here as written, but this requires the washer method, which we're not doing yet in this video. So I'm going to alter the problem a little and say here, x equals 0. And now we can do this with the disk method. So I got to re-record all this. And hopefully I've cut the video up, right? So you're not seeing the other one. All right, so let's draw this guy out. We've got, everybody's positive here, so I don't have to draw all of 2x cubed. I'm just going to draw this chunk over here up to x equals 1. And I want this region here between x equals 0, x equals 1. By the way, when I plug in x equals 1 here, I get y equals 2. So we could even say here, and y equals 2. This region rotated around the y-axis. So maybe we'll draw in the mirror image here. And we'll draw in some of our disks. So like there's a disk, here's a disk. Maybe we're up here at height y. Now remember, this is important when you're using the disk or washer method, because they're really the same method. If you're rotating around the y-axis, everything's in terms of y's. Everything. Your function, your limits, your dy. If you're rotating around x, everything's in terms of x. If you're rotating around y, everything's in terms of y. When we get the shell method later, that's all the opposite. For now, for disk and washer method, if you're going around the y-axis, everything needs to be in terms of y. Meaning I need to find this x in terms of y. I need x to be some function of y. So we've got, y equals 2x cubed. Move the 2 over, y over 2 is x cubed. Take the cube root of both sides. I'm going to write this. So we're taking cube root of both sides. I'm going to write this as y cube root of y, or let's write it as y to the 3, the 1/3 over 2 to the 1/3. And that's going to equal x, which was my function of y. My limits my smallest washer up to my biggest, or my I should say bottom to top washer. This is y equals 0. This is y equals 2. Okay, then we know volume is going to be the integral from c to d, smallest to largest y values, pi g of y squared dy. And again, like if you understand what's going on here from a conceptual standpoint, it's not about memorizing formulas. This pi r squared, that is, this is r, which is a function of y. That r there is the radius of this circle. So this pi r squared is the area of this circle, which has a little thickness delta x, and we're adding all those up. Remember, an integral is just a sum. We're just adding a bunch of stuff up. Okay, c and d here are my starting and ending y values because everything's in terms of y. So this will be the integral from 0 to 2 of pi. Here is g. So here I'll write it like this: 1/3 2 to the 1/3 all squared dy. So that's going to be, I can bring the pi out front. And in fact, I can bring this guy out front. I'll have 2 to the 1/3 raised to the second power. That's 2 to the 2/3 power. And then here in the integral, I'll have y to the 2/3 power dy. So make sure you understood all that. Like go through the steps, check, make sure you understood that. Antiderivative, just using power rule here. So I'm going to raise this exponent up by 1. 2/3 plus 1 would be 2/3 plus 3/3. That's 5/3. So I'm going to have here y to the 5/3. And remember, you're supposed to divide by the new exponent. So this would be divided by 5/3. But dividing by a fraction means multiply by the reciprocal. So that'll be times 3/5. Evaluated from 0 to 2. At 0, this is 0. Why? 0 to any power is 0. So we just got to plug in the 2. That's going to be pi over 2 to the 2/3 power times 3/5 times 2 to the 5/3. Just plugged in the top. And technically here, I'll write it minus 0. Because 0 to any power is 0. All right, now we just got to clean up a little bit. 2 to the 5/3 divided by 2 to the 2/3. So a little bit of side work here. Subtract the exponents. That would be 2 to the 3/3, which is just 2. So this and this will cancel down to just 2. So I'll get 2 times 3, 6 pi over 5. Okay, now this is kind of interesting. Like real quick, I'm almost done here. The question that was asked in the book was not this volume. It was this region. And see, I did this region in here rotated around. They had this region rotated around. So I already went through this and I got the wrong answer and I had to figure out, oh, well, I would have to use washers to do that. And I don't want to do that in this problem. But we could actually answer this question here as asked using the answer we just got. Without having to go through the washer method, I could find now the volume of this little region rotated around if we think about this. So real quick here. I've got this guy here that I'm rotating around. If I consider it's up to 2, an entire cylinder. So everything here, we're all the way around. This cylinder, so that's some cylinder. You know what I'm trying to draw there. Has height 2, has radius 1. This was 1. The volume of that entire cylinder is just pi r1 squared times height. That's just 2 pi. The volume inside here in the blue, so this volume, the one we just found, so I'll write that here, just found, that was 6 pi over 5 cubic units. So the one the question asked about was this region rotated all the way around. The blue and the red have to add up to this. So the red is just the black here, 2 pi, minus the blue, 6 pi over 5. Well, 2 pi is 10 pi over 5. So that would be 10 pi over 5 minus 6 pi over 5, which is 4 pi over 5. So the point I'm making right here, this question from your book, technically you need the washer method to solve that, which we haven't learned yet. But we could find that same thing by doing the disk method, finding the entire volume of the whole cylinder and subtracting out the part we just found to get what's left over. That's literally what washer method does. Washer method's coming up in one of the next videos. That's what washer method does. To find some inside kind of region, you just cut out the parts you don't want. That's what washer method is. So this is some nice foreshadowing, and that's a good place to stop.